Okay, welcome to MSCF Python Programming Basics, Week 2. In Week 1, we introduced the idea of values of different low-level types, int, float, stir, bool, and the special value none. We also talked about variables with assignment of values into variables. We took a look at certain arithmetic operators, how to define and call simple functions. Then we took a look at equality and inequality and relational kinds of operators that we were able to use to make if, elif, else decisions and also to write while loops. Now in Week 2, we're going to introduce the built-in so-called collection types that Python provides, namely the list and tuple. A list is very similar to a vector or an array in other languages. That is, it just has a sequence of values accessed by integer subscripts. A tuple is similar, except that the items within a tuple can't be modified, whereas the items within a list can be modified. We're going to take a look at for loops, which is a second kind of loop that we can use to step through the items contained in a collection. And then a couple more, somewhat more sophisticated collection types, the set, which behaves very much like a mathematical set, and the dict, or dictionary, which allows you to define mappings between keys and associated values. All right, so a list, for example, associates an integer index with a value. So we have item sub 0, item sub 1, item sub 2, and so on. But in a dictionary, you can be more flexible with the keys. So you can use strings for keys and do things like mapping from a user's name as a key to that user's email address as an associated value. So that's what we're going to take a look at here in Week 2. Let us commence. Okay, so a list can be defined by typing a sequence of item values in square brackets. And here on the right-hand shell screen, I'm going to type in this first example. V, which I use V for vector, gets a list consisting of 7, 2, 3, and 0. Okay, so this list happens to contain all int values. I could also have a list of float values or a list of string values. Actually, I can have a list of mixed data types. So I could have a list containing ints and floats and bools and strings and so forth. Interesting. Okay. I forgot my comma there, so good. All right, so let me do this correctly. 7, 2, 3, 0. Okay, so V is now a variable that refers to this list containing 4 items. The items are indexed from 0 up to 3 in this case. So I can access an individual item by saying V sub 0, which will get me the 7, V sub 2, which will get me the 3. To see the entire list of values, I can just type the name of the list itself, and the Python shell will display that list to me. Now, I can also, I missed this part, so let me be clear about this. I can access items in reverse order by using indexes from -1 for the last item in the list to, in this case, -4, which would be the first item in the list. All right, so V sub 1 is using a non-negative index. V sub 1 is going to be the 2. V sub -1, on the other hand, is the final item in the list, whose value is 0. V sub -4 is the first item in the list, 7. If you try to access outside the bounds of the list, you will get an error, specifically an index error. So V has 4 items in it. If I ask for V sub 5, I get told that that's a bad index. If I ask for V sub minus 10, likewise, I get told that's a bad index. So the valid indexes for this list V are either from 0 to 3 or from -1 to -4. A list is what's called mutable. That is, the items in a list can be modified. This may seem sort of obvious. I mean, good heavens, why couldn't you modify the items in a list? But we'll discover some other types later, specifically tuple, that are not mutable. Once you've created them, you cannot change the items that they contain. So here's my current V, the 4 items 7, 2, 3, and 0. If I say V sub 2 gets a 5, that is actually going to change the value 3 to the value 5. Okay, so V now contains 7250 instead. And here at the bottom of slide 4, I have another example of a list, this time containing mixed data types, 5, high, true, 3.1415, and none. All right, so this is perfectly reasonable as well, and I can also access the items in here. So V sub 1 is going to be the string high. 2 of the arithmetic operators are defined for list objects, although they don't do, the plus does not do addition, and the star does not do multiplication. What they do instead are concatenation and repetition, respectively. So I have this list, V, currently containing 7250. If I say V plus some other list, 1, 2, 3 in this case, I get the concatenation of those 2 lists. All right, so that's a single list containing 7250, 1, 2, 3. Now, that took the current contents of V, a copy of it, and appended the contents of the list literal 1, 2, 3. This did not actually change V. If I wanted to change V, I would have had to assign that result back to V. Okay? V still contains 7250. If I say V star 2, this means repetition. So that list is going to that list is going to be repeated twice. And so the resulting list has 8 items in it, 7250 followed again by 7250. Again, this did not actually change V. Here's a cool thing. If you want to have a list of some huge number of zeros or some huge number of ones or whatever, you can use repetition on a list containing a single item. So here, by saying a list of one item 0 repeated 10 times, that gives me a list of 10 zeros. For example, I might need such a list to count various occurrences of 10 different possible input occurrences, let's say. Now, a long list can simply be split across multiple physical lines because the list is contained in square brackets. You may recall that we said if we have parentheses, we can split a logical line across physical lines without bothering with the backslash at the end of the line. So here, because the print function call has parentheses in it, I can go ahead and type out the arguments being passed to print on multiple lines. There we go. And similarly for lists, I can say V2 in this case gets 1, 2, 3, 4, and if my list is too long to type on one line, I can just continue typing on the next line down. Now, in slide 6, I indented things further just to make things look nice. That's not actually necessary. You can just go ahead and continue typing at the point where the shell automatically puts your cursor, wherever that is. 9, 10, 11. Actually, it's fine if I have extra spaces in here. That's not a problem either. And so here now I have created V2 as a list of 12 items, all of which are int V2. Okay, so there is V2, which I've defined on multiple lines. To step through all of the items in a list, I could use a while loop. I could say idx, let's say, gets 0, while idx is less than 10. Remember that the indexes go from 0 up to 9. Sorry, this has 12 items in it. So I'll say 0, idx less than 12. So the indexes go from 0 up to and including 11, but not 12. Print idx and v2 sub idx. All right, so this will print out all of the items in v2. I had better remember to say idx gets idx plus 1, or I've created an infinite loop. Okay, so that is one way of stepping through the items in a list, but a more convenient way in many cases is to use the for loop instead. If I say for some variable, might as well use idx again, in some iterable, okay, now a list is iterable. That is, it's able to be iterated through. And here I'm using the hard-coded list 1, 5, 9, minus 4, 12. I'm having remarkable difficulty typing here. All right, so here I've got a hard-coded list of 5 items, and this loop variable idx is going to be set to each of those items, one item at a time. Now that's different from what I did up here. Here I said idx was integer 0 up through integer 11. Down here, idx is going to be set to 1 the first time through, then 5 the next time through, then 9 the next time through, and so forth, which, it occurs to me, means that idx is a stupid variable name. So let me call this val instead. So for val in this list, 1, 5, 9, minus 4, and 12, let's print the value, and then let's print a string containing a couple of spaces, and then let's print the value squared. Okay, so here we have these 5 values in the list with their squares after some spaces. All right, so that's what the for loop is about. A string, is also an example of an iterable. So we can also use a for loop to step through the items in a string. If I say for s in howdy, okay, howdy is my string. I've used single quotes. I could have used double quotes. I could have used triple single quotes or triple double quotes. It doesn't matter. I'm just going to print s. Now, when you use a for loop to iterate through the items in a string, what you get are the one-character substrings within that longer string. So the first time through, I'm going to get the string h. The second time through, I'll get the string o, and then w, and d, and y. All right, so that string has 5 one-character substrings within it, h, o, w, d, y. And just to repeat, a string is another example of an iterable. A third example of an iterable is this nice thing called the range function. Now, the range function gives you a convenient way of counting through a sequence of integers. If I say for, let's say I in range 10, range 10 is going to yield the values 0, 1, 2, etc. up through 9. The range here, the argument, if I give just one argument, is
beyond the end of the range. All right, it's one past the end of the range. So if I say for I in range 10, print I, that's going to print the values 0 through 9, but not 10. I can specify 2 numerical arguments in the range, and the first argument will be treated as the beginning of the range rather than 0. The second argument will be treated as the end of the range, that is the value that's one too far. So if I say for I in range 5, 10, and I could put spaces in here if I want, doesn't matter. That means that the first item is going to be 5, and then I'll get 6, 7, 8, 9, but not 10. Okay, so with one argument, I automatically start from 0, and the value that I specify in the range is the value that's one too far. With 2 arguments, the first value is the start, and the second value is one too far. I can also specify a third value as well, which is treated as the step size. The default step size is 1, so if I say for I in range 5, 10, 1, this is going to behave exactly the same as if I had said for I in range 5 through 10. All right, I get the values 5 through 9. But if I say for I in range 5, 10, 2, now I have a step size of 2. That means that the first value displayed is a 5. The second value displayed will be 2 plus that, so 7. The third value will be 2 plus 7, which is 9. Now, the fourth value would be 11, but 11 is too large, and we only print values less than 10. So this is going to produce 3 lines of output, 5, 7, and 9. All right, so that's a very convenient way, a very convenient iterable for stepping through a sequence of integer values. You can also count down. Okay, so the first example here for I in range 5, essentially I did I in range 10. You can also count down by specifying a negative step size. So let's suppose I want to count from 4 down to and including 0. Well, if I want to include 0, that means that the value that's one too far is minus 1. And I'll specify a step size of minus 1 as well. And what did I do wrong? Oh, I forgot to say 4. For I in range 4, minus 1, minus 1. Okay, so for I in range, starting from 4, down to but not including minus 1, with a step of minus 1, print I. And this is going to give me 4, 3, 2, 1, 0. All right, so you can use the for loop with range. Well, particularly you can use range to create for yourself an iterable that counts up or that counts down. Len is a built-in function that will tell you the length, the number of items in any sequence. These 3 iterables that we've just discussed, namely the list, the string, and the range, are also examples of sequence data types. And so if I ask for the length of a list, here I have a list containing 3, 2, 4, 4. Well, of course, the length of this is going to be 4 items. If I ask for the length of hello, I'll be told the length of that is 5 items. And I can also request what is the length of a range. If it's not obvious, I might be interested in knowing how many values this range is going to yield. I'm starting from 10. I'm going up to but not including 20. I guess if I were a little bit smarter, it would be immediately obvious to me how many values that is. But rather than calculate it, I'll just ask the len function to tell me. Okay, so there are 4 values within that range. All right, so here on slide 12, I have another example involving a range as well as len. V3 is a list that in this case happens to contain 5 values. We're not dwelling on this, but it happens to be the first 5 prime numbers. And I'm saying for I in range. Okay, I want to display starting from the last one of these down to the first one of these. So the index of the last one of these is going to be the length of the list minus 1. Okay, this list has 5 items in it, so the length is going to be 5. But remember that the last index that's valid is 4. So length of V3 minus 1 is going to be my 4. I will count down 2, but not including minus 1, with a step size of minus 1. And what I'm going to do is to display a string telling me what... Actually, I want to display both the index and the value at that index. So I'm going to say v3 square bracket as a string, and then I as my index value, then close bracket and colon as another string, followed by v3 sub I. All right. And so here I get my 5 lines of output counting backwards from v3 sub 4, which is the 11, down to v3 sub 0, which is the 2, and of course not including v3 sub minus 1. So we've looked at how to create lists using square brackets. We've also looked at how to access items within list, again using square brackets with an appropriate subscript. The list data type also supports 11 named operations, which in object-oriented lingo are called the methods for the list class. And you should know these. I will assume that if I ask you about these methods, that you know what they're called, what arguments they take, and what they do. First of all, we can append an individual value to a list using the append function. We can eliminate all of the items from a list using clear, and we can make what's called a shallow copy of a list using copy. If we want to know how many times a particular value occurs within a list, we can use count for that purpose. Extend is a little bit like append. The distinction is that extend will lengthen the number of items in a list according to some iterable, which might be another list or a range or a string or some other kind of iterable, whereas append only appends a single value to a list. We can also find out the location, that is the index within the list of some particular value. We can insert a value at some arbitrary location within the list using the insert function. Now, this is, again, somewhat like append, but append always puts the new value at the end of the list, whereas insert is more flexible. It's able to put a new value anywhere within the list. We can pop a value from the list. Now, that will actually remove the value from the list and return to us what that value is. I can specify an index if I wish to. If I don't specify an index, then I automatically pop the last value from the list. I can remove a value from the list without returning it by saying remove val. I can also convert the list to reverse order with reverse, and I can sort the contents of the list by default in ascending order using the sort function. Okay, so here are several examples. I have V still containing 7250. If I say v.append a value of minus 6. This adds the value minus 6 at the end of the list. Whereas if I say v.insert at some index 1, in this case, a minus 6. Now, index 1 is the index of the 2. And the index specifies the value ahead of which, or the position ahead of which, the new value should be positioned. So I'm going to insert this new value minus 6 ahead of the 2. All right, so I started out with 7250. I appended minus 6 to the end of the list, and then I inserted minus 6 ahead of subscript 1, that is ahead of the 2 in this list. If I want to know how many minus 6's occur within this list, I can count them. If I count something that doesn't exist, I should get a 0, so I'll count the number of 123's, and indeed I do get a 0. The sort member function, by default, will sort the values in the list. Now, I said in ascending order. Technically, this is non-descending order. And so the 2 minus 6's become the first 2 items in the list, followed by 0, 2, 5, 7. If I say v.pop, and I don't give any argument for pop, that's going to give me back the 7 as my return value. That return value is displayed by the interactive shell. Also, that value 7 is removed from the list, so the 7 is no longer at the end of the list. I can specify a value that I want for the index to pop. And if I say v.pop sub 0, that's actually going to return to me and remove the first minus 6. Okay, so the second minus 6 is still there, as well as the 0, 2, 5. Clear eliminates all of the items from the list. The list still exists, but the list is now empty. Okay, so v is empty, but if I say v.extend, and here I specify an iterable, 4.4, 1.1, 2.2. Recall that a list is an iterable. That will extend the list to contain all of the items within this iterable. So now v contains 3 items. I'm not limited to extending a list using a list iterable. If I say hi, well, recall that hi, a string, is also an iterable. As an iterable, what's going to happen is that this list will be split up into 1-character substrings, and what I end up with is the list extended by an h as well as an I. And furthermore, I can extend the list by a range, 2, 5. So now the values 2, 3, 4, but not 5, are also going to be appended to the end of this list v. Since these data types are not the same, they cannot be directly compared to each other for order. Now, the floating point numbers, 4.4, 1.1, 2.2, and the integers 2, 3, 4 certainly can be compared for order, but the strings h and I cannot be compared with the numbers. So if I try to do a sort of this list, I get an error message, a type error. So sorting this list that has values that can't be compared with each other ends up not doing anything, although you can't count on that being the case. If I say v.remove an h, then the h is eliminated from the list v. v.index I will tell me the subscript that I is located at, which should be 3. If I say v.pop that item, then the I is no longer within the list. All right? And at this point, since I only have numbers remaining in the list, and those can be compared, I can now sort the list. And I have 1.1, 2, 2.2, 3, etc. Okay, so those are examples of the named methods that you can use to access and modify and find out about the items that exist within a list. Okay, so we have been using variables to keep track of values. It's time for us to be really more clear about what variables are. It turns out that a variable in Python is a reference to a value, specifically a reference to an object. And unlike many other languages, the variable itself does not have a particular data type associated with it. And in fact, it can change over time which types of objects it refers to. If I define a variable I, and I say I gets 123, that creates the variable I, or reuses the variable name I if I had already existed, and causes I to refer to an int value of 123. And I can use the type built-in function to see that I is currently referring to an int. But it's fine for me to change I to refer to a different type. If I say I gets 2.7, now the type of thing that I is referring to is a float. And if I say I gets high in quotes, now the type of thing that I is referring to is a stir. If we take a look at what's going on in memory as a result of these assignment statements, it looks like this. We start out with this int value 123. When we assign 123 to I, that creates or reuses the variable name I to refer to that int object in memory, 123. When I then say I gets 2.7, that causes a value 2.7 to be stored in memory, and the name I is changed so that it refers to 2.7 now. In fact, assuming that there is no other variable existing referring to that 123, that int value 123 can now be reclaimed from memory by your Python shell, by your Python environment, so that that space could be reused for some other object. Then when I say I gets high, space is set up in memory for that string high, and I is modified to refer to that string. 2.7 now, unless there's some other variable referring to that value, has no references and so can be reclaimed from memory. This is a critically important thing to understand, is that variable names in Python refer to objects in memory, and if an object has no variables referring to it, the memory space for that object may be reclaimed to be reused for some other object later. Now, it turns out that in Python, almost anything is an object. Depending on what other languages you have used, this may be what you were expecting, or it may be somewhat beyond what you're expecting. So the low-level data types like int objects, float objects, bool objects, and so forth are objects stored in memory. Likewise, a list or a tuple is an object stored in memory. Next week, we'll take a look at sets, which are objects stored in memory, but also a function like our factorial function or the Fibonacci function that you wrote are objects stored in memory. A class, that is a user-defined data type, is also an object stored somewhere in memory, and so forth. Now, each object is guaranteed to have a unique ID number, and that may or may not be the memory address where that object is stored. you can learn the ID number of an object with the built-in function ID with that object as an argument. So for example, a constant is an object. If I ask for the ID of 7, I get told the unique ID number for the int value 7. Specifically, what number you get is going to depend on your system. I got 140 blah 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 168. If I now say x gets 7, this creates a variable x referring to the object 7. And if I ask for the ID of x, well, what I'm really getting is the ID of the object 7 that x refers to. And so that's the same ID number that I just saw. And if I say y gets 7, similarly, I get the same ID number when I look at y. Okay, so I have one object, this int object 7, and currently I have two variables, x and y, referring to that object. If I say z gets x, this sets up a new variable z referring to the object that x refers to. So z is not currently referring to the variable name x. Z is referring to the object whose value is 7. And if I ask for the ID of z, once again I get that same ID number. Now, small integers have the interesting property that they seem to remain at fixed locations throughout the execution of your program. So if I say w gets 18, well, 18 is a small integer object. W is referring to that integer, and that integer has this particular ID. If I say w minus gets 11, this is equivalent to saying w gets w minus 11. And so now the value that w will be referring to is a 7. And in fact, since 7 is a small integer value which already has a location, if I now ask for the ID of w, if I could type, if I now ask for the ID of w, I will get the same ID number that I have for the 7 that I started out looking at on slide 21. Okay, so 7 is at a fixed location in memory. 7 is an object that doesn't move around, and it and any variables that refer to it all have the same ID. This is not going to be the case for large integer values or for floats or for various other things. It's not guaranteed that the ID of 7 is always going to be the same number for all possible references to 7. Here, for example, if I create I to refer to some big integer value, I'm just going to type some stuff here, and ask for the ID of I do get some ID number. If I now say j gets I minus 5, okay, j is a variable that refers to some object that is different from the object that I refers to. So if I ask for the ID of j, of course that's some different value. If I say k gets j plus 5, the reference k now refers to an object that has the same value as I, that is, as the object that I refers to. So I started out with I subtracted 5, and I added 5. So k is clearly referring to an object with the same integer value that I has. And yet, even though k is equal to I, it turns out that the ID of k is not the same as the ID of I. I can compare this directly. I can say idk is equal to id I, and I get false. Okay, so sometimes, and particularly in the case of small integers, it turns out, at least in my system, my environment, that the ID numbers for small integer values remain the same. But for larger values, those ID numbers can change. And what that means is that my Python environment has got this big integer value, 9812, blah, blah, 3984, stored at some location in memory. And my Python environment has chosen, when k is created, to allocate that same value as a separate object somewhere else in memory. Okay. Lists are also objects. If I say v4 gets 1, 2, 3, that is an object stored in memory. And it turns out that independently defined lists are different objects, even if the values that they start out with are the same. So if I say v5 gets 1, 2, 3, okay, even though the values of the list that v4 refers to are the same as the values that the list v5 is referring to, it's definitely going to be the case that v4 and v5 are separate objects. That's a feature of the list object type, the list class. If I, on the other hand, say v5 gets v4, all right, now let's think about this. So v5 is a variable referring to a list containing 1, 2, 3. But when I say v5 gets v4, that means v5 is no longer referring to the list 1, 2, 3 that it was set up to refer to. And instead, v5 is now referring to the same object that v4 is referring to. And I just observed that there's a typo in my slide 24 here. Rather than ID n, there's no n around here. This should be ID of v5. All right, so now ID of v5 is the same ID as v4. In week 1, we talked about the is equal to and is not equal to comparisons of values. These can be used for lists. I can ask whether v4 is equal to v5 by using the double equal sign, and that's true. But that does not imply that v4 and v5 are the same object. It only implies that the object's values are equal. Now, in this case, it does happen to be the case that v4 and v5 are the same object because of this v5 gets v4 that I just did. But let's start over again with v1 being a list containing 1, 2, 3, or referring to a list containing 1, 2, 3. v2 being a list containing 1, 2, 3, or referring to that list. At this point, we know that v1 is equal to v2. That is, these lists have the same number of items, and the items are all equal to each other. Therefore, the two lists are equal. However, it is not true that v1 is v2. The ID of v1 and the ID of v2 are different. If I say v3 gets v2, that causes v3 to refer to the same object that v2 refers to. And if I now ask whether v2 is v3, this is true. So this can be a little bit difficult to keep track of. Having lists whose lengths are the same and whose item values are the same does not imply that they are the same list. They may be different lists from each other. And you can use is and is not to compare the object IDs of the objects that variables refer to. Now, another useful test to know about when you're dealing with lists is in and not in. All right, so I have V1, which refers to a list containing 1, 2, 3. If I ask whether 2 is in V1, that's true. If I ask whether 8 is in V1, that's false. All that's necessary is that the object to the right of the in, or the not in, be a sequence or some kind of collection. So, for example, I could also ask whether H, that is the capital H, is not in the string hello, where hello has a little h in it. This is going to be true. I can ask whether 4 is in the range of 10. All right, now here, range is a function. Range is an iterable. It's not an object, and yet it's fine for me to ask whether 4 is in the range of values produced by that iterable. And so 4 is in range 10. These 4 new Boolean operands that we've introduced, is not, in, and not in, it turns out all have the same precedence as the equality and relational operators that we introduced last week, which in turn is at a higher level of precedence than the logical not, the logical and the logical or. An object that exists, that is, an object that has at least one reference, occupies memory. And we have a finite amount of memory on our systems, even though that amount of memory may be very large. If you want to make sure that an object is no longer occupying memory, one thing that you can do is to assign none to the reference to that object. All right, so I have V1 referring to this object, this list object containing 1, 2, 3. If I say V1 gets none, now V1 no longer refers to that list 1, 2, 3, and the memory for that list can be deallocated. Since V1 now refers to none, I will have to use print in my interactive shell in order to see that value for V1. This is particularly useful if you have really large collections of data. Here I have V being a list of 1,000,000 zeros. Well, I'm not going to wait for that to print. All right, I'll hit Control C. So V is referring to a very long list, and you don't want to make the mistake that I made of attempting to display V. But if I simply say V gets none, now V exists, but it no longer refers to that long list, and so that list can be deallocated for other use. Another thing I can do is to eliminate the variable altogether by saying del of the variable. If I say del V, then the name no longer exists. And of course, if that name was referring to some object, that object would no longer have references and the memory could be deallocated.